I started recording.
Okay, so hi everyone, welcome to Graphics Programming Virtual Meetup. And today we will talk about this shiny new fourth edition of physically based rendering. We plan to read through all the book, and probably we will rotate and just have different people to talk about different chapters. And yeah, today we will just talk about what's inside this book by work through chapter one. And so yeah, for people who don't know, physically based rendering is obviously about physically based rendering, and it's described a code base called PBRT, which is available on GitHub. How to go to 1.1. So this is about how this book works. So this book uses a technique called literate programming. So the book has wall of text, but also some code. Sorry, someone have echo. Also some like code inside. And the interesting thing is it have code blocks, code blocks with those like those fragments where they can write some text here and then define it later. So this is basically how this book works. I, I guess this way they kind of can like decompose a function into a small blocks without writing some additional functions. And 1.2 talks about photorealistic rendering and ray tracing algorithms. First, it talks about something about history, like what is light. And nowadays, people feel like light is both a wave and a particle. Is a particle. Yeah. So it's a wave and a particle, but it's so complicated. So we don't deal with that. But instead, we instead we just work with a simpler model, sometimes called geometric optics. And this leads to a more efficient computational approach called ray tracing. And there are a lot of things to say about ray tracing, but it usually have at least the following objects and phenomena, like a camera, ray object intersections, light sources, and visibility check, which is trivial in ray tracing because we can just send a ray. And light scattering at surfaces. So yeah, when light hit a surface, it need to do some scattering, and we need to describe how it gets scattered. Indirect light transport. I feel like those two are highly related. And ray propagation, which usually when doing a vacuum, it's nothing happened, but when ray pass through some more interesting media, then something can happen. And then it start to talk about individual component of ray tracing. We have first camera and film. So one simple model of camera is so-called pinhole camera. Even though in computer graphics we usually don't deal with something like that, but have a film in front of our hole, so we don't have this opposite. Yeah, we have this usually. We have a film in front of the hole at the image plane. And the hole is renamed to the eye. And then the issue is at each point in the image, what color does the camera record? So this is determined by which part of scene is visible at that point. And for that point, we need to put a ray, we need to send a ray into that point. So the important task of camera is to generate rays, at least for ray tracing. For some camera models with lenses, then the calculation of rays is more complicated. Also, light arriving at the camera along a ray will carry different amount of energy at different wavelengths. In most camera sensors record RGB. Camera imperiality also include a film abstraction that both stores the image and models the film sensor's response to incident light. I'm not sure what that means. But I guess we will see.
Yeah, not all cameras have the same like sensors. So like to convert a light to, an RGB triplet, each sensor will behave slightly differently. Right.
It's like tone mapping.
I guess sort of. I mean, you're converting. The goal of the sensor and the camera is to convert like a spectral mixture of light, into some sort of like color that can be digitally, like discretely stored.
Would this also include the filter used, like if you're gonna use like a box filter or something, or
Yeah, so the sensors are, I don't know, it's kind of complicated. It's like a lot of like transforms, if you will, that happen to the light before it's even turned into like a discrete signal.
Interesting. I guess we'll see it in chapter 4.6. Yeah, also ray object intersection. Yeah, basically giving a ray how to it intersects objects. And I guess this is a sphere. Yeah, it's a sphere. And the intersection point alone is not enough. We also need to know some other properties. We need to know the material and some additional information like the normal. And yeah, PBRT require even more information like partial derivative of position surface normal. I guess this thing is very large, so it has tons of triangles. So I guess next talk about acceleration data structures. Yeah. Next topic is light distribution. So intersection stage give us a point and some information about that local geometry. So our goal is to find the amount of light leaving this point in a direction of the camera. So rendering equation then. And also, but also we need to know how much light arriving at this point. This involves both geometric and radiometric distribution of light in the scene. For very simple light, we only need to know the position of the light, but also point light does not exist. And we usually deal with error light. I guess I will not read this in detail for now. And also the light distribution, with light distribution, we also need to consider the visibility. But yeah, it's easy to calculate visibility by just sending a ray to the light source and see if whether it get occluded. And those kind of rays are called shadow rays. And also there is light scattering at surface. where each object in the scene provide a material which is given by this BRDF. But yeah, also some material have subsurface scattering, so we need this kind of BSSRDF. Yeah, also indirect light transport, so we need to talk about things where light transportation is recursive, where it bounce off and do the same kind of thing again. So yeah, early style weighted ray tracing is very good to simulate this kind of mirror reflection. So and yeah, but more modern version is better at models light scattering. Oh, here is a rendering equation. And for ray propagation, yeah, when ray pass through those kind of media where there are a lot of particles, volumetric media, then some interesting things happen, then we need to handle that. And PBRT system review, and this is chapter 1.3. PBRT, by the way, you can find it on GitHub. And there's a chat. And I encourage you to play with it. And it follows an OOP implementation. At least that's what V3 did. So this version also, I assume, did kind of similar things where there are a lot of interface type, and then there are implementation based on that. And but also to support GPU approach, I think they made some interesting change that they use a tag-based dispatch. I guess this is different from PBRT v3, where they no longer use inheritance.
They really love virtual functions in the previous version.
Yeah. Oh, no virtual now. I guess
Comment that they have medium and light next to each other, and I know that medium refers to like media and light refers to like things that emit light, but I really wish there was something just named dark. So you got dark, medium, light all together.
Or heavy.
Yeah, or heavy. Yeah. My puns are no bounds.
Okay, they use a tag-based dispatch now. And yeah, they will talk about it more later. And GPUs, nice. I think they use NVIDIA optics.
Oh yeah, it's capable of running on GPUs that support C++17,
Yeah,
which yeah, CUDA, I guess. Or
Yeah, is it just CUDA or?
Well, optics uses
CUDA.
CUDA, but
Yeah,
I think,
optics is based on CUDA.
but yeah, that's the only programming environment I know of that can run C++ on GPU. Like, I guess, yeah.
It's really nice, but yeah, but also NVIDIA only.
Yeah, I guess it would have been a lot of effort to make it like run in trading languages or something. It's a, I guess GLSL especially has so few language features.
Yeah, there are something only works on the CPU, or maybe they just haven't implemented that on GPU. So people, I think those university courses, they use PBRT as a starting point and then extend it into various things as student project. So conceptually, PBRT have three phases of execution. First, it parses the scene. And the results of the parsing phase is an instance of basic scene. That sounds more like the Steve Papa standard library, like basic screen. What? Oh, which stores the scene but not suitable for rendering. And in the second phase, it creates specific objects for the scene. For example, camera. Yeah. Previous version of PBRT does not care, but now the CPU and GPU have different ways to represent things. And the third phase is the main render loop. And to orchestrate the rendering, PBRT implements an integrator because the main task is to evaluate an integral of the rendering equation. is mainly boilerplate parsing CLI argument. And yeah, parse the scene file, and then this is the main thing, I guess. And it just renders either CPU or GPU. I guess they use a wavefront render on the GPU. So I hope it has more symmetric name though. Integrator. Oh, this is only a base class for the CPU implementations. So again, virtual. It takes a single primitive that serves as the root of all objects, as well as an array of lights. Aggregates are basically an acceleration data structure that stores everything. And each light source in the scene is represented by an object that implements a light interface. Oh, interesting thing is that they are not using like pointer references for those. Does that mean it's used the like tag approach? Yeah, I guess so. Tagged pointer. All right. So we have a bound of the scene. We also handle lights, and specifically infinite lights. This is maybe too much for us to read through in this week. Do we want to read through this?
I think a lot of it is just a very high level overview of the code flow, and then some of the same things that would be going into much more detail in the actual chapters.
Yeah, so maybe let's stop here.
I mean, Is there anything in the fourth, before we stop, is there anything in the fourth version that we want to look at that is just new and different than the third version?
Yeah, I was curious,
No,
is
this
there like a list of all the
act-
changes? 'Cause, like I know the GPU stuff's big, but I'm curious with like all the more pure theory chapters if there's been any changes.
well, one thing I immediately noticed when I looked through this is they moved this to very early, and I like that.
The GitHub has a features of major changes. So,
Major changes.
yeah.
Vector. Nice. These are nice. And modernized volumetric scattering with a really new paper. Yeah, support on GPUs, new materials. Light sampling improvements.
That's a lot of good stuff.
Yeah, a lot of good stuff.
Ooh, that's a small thing, but that's really nice that you can use absolute physical units for everything instead of just
Yeah,
arbitrary math number.
yeah. I want to know how it looks, though. How it looks in code. But yeah, we will probably talk about it someday.
Ooh, that last one is a really neat usability feature. Not really related to the teaching, but the TEV image viewer, where it will pipe the in-progress output to like a port, and so you can just
Where?
display the image as it renders.
Oh,
For reading through the book, I don't see how that's going to be that practical, but for actually using it, that's going to be really nice.
yeah, but I assume if you want to read through this, you probably will play with the code base, right?
Right, right.
So yeah, this will be useful.
Oh, that's it.
Very nice.
Oh, that's even. It's like not just an image view, but like a whole, you know, basic image editor view, the exposure, offset, do some other stuff. That's really cool. Okay. Well, that answered my question about what changed and what's to look forward to.
But that's just features. For
Right.
other things, yeah, I think I like this. Uh, this chapter looks the same. The same. I don't spot. Yeah, I don't spot anything obvious
Yeah,
apart from this, obviously. Yeah.
the thing that kind of only makes sense on a GPU is a new thing.
Yeah.
Yeah, I really like the Monte Carlo as the second chapter because that's just such a important topic for everything.
Yeah.
And it's true that the book takes 7 or 8 chapters to get to cover all of the necessary components, but that are needed to actually render anything. And yeah, technically you can render without Monte Carlo, but what's the point? When you're trying to do physically based stuff, you really do want that statistically.
No, we just stuck with weighted rendering basically. If
Yeah.
we don't do any Monte Carlo, yeah.
Okay. So do you want to stop?
We start.
Stop the recording?
Yeah.
Okay.